Next we are going to study the construction, the principle and the working of the moving coil galvanometer. Moving coil moving coil galvanometer is a very sensitive instrument used for the detection and measurement of small electric current. Here the working of the moving coil galvanometer is based on the principle. That principle that we have already seen, that is, when a conductor carrying a current is placed in a magnetic field, it experiences a mechanical force. You can see there is a magnetic field that is represented by the blue dotted line, blue lines with the arrowhead, and a conductor is placed, and I is the current flows through the conductor, and suppose L is the length of the conductor, and also here there is an angle theta that made by the conductor with the direction of the magnetic field. In that case, the force acting on that conductor is BIL sin theta. BIL sin theta. And the direction of the force is given by the Fleming's left hand rule. Okay. So this principle is used in the working of the moving coil galvanometer. Now we are going to see what are the main parts of the moving coil galvanometer. This galvanometer essentially consists of a flat coil of insulated copper wire that is wound on an aluminum frame. It is suspended by a phosphor bronze wire between the pole pieces of a powerful horseshoe magnet. Okay, so this phosphor bronze wire, and this coil is suspended between the two pole pieces of a powerful magnet. In order to make the magnetic field radial and arrange that it is always parallel to the plane of the coil for all positions of the coil, we are placed a soft iron block is placed at the center of the coil without touching them. Okay, a soft iron core is placed inside this coil, which is mounted on a aluminum frame. So this core is soft iron core is placed without touching this coil, and the current to be measured, that is, enters through the coil through the suspension wire, and here leaves through a spring strip below the coil. Here it is enters the current and it leaves the current, and you can see there is a small mirror is attached on the suspension wire. This is for the measurement of the deflection. Okay, that we can see later. Now this is the main parts of the moving coil galvanometer. Now here the coil that we can represent by the PQRS. Coil is PQRS. It has a n number of turns. It is not a single turn. It has a n number of turns. And the length of the coil of this frame, the length is this frame is L, and B is the breadth of the coil. Okay. So when a current I passes through the coil, now we have a current carrying conductor. It is placed in a magnetic field. So when a current I passes through the coil, what happens? Each side of the coil experiences a force. Let us see. Here, let us first consider the length part of this coil, that is along SP. Okay. Now the current flowing in the clockwise direction. Let us say that is current flowing through the the clockwise direction. Now that is the direction of the current, and the field is directed from north pole to south pole. Okay, so what is the force? We know the value of the force is BIL sin theta. Okay, here the conductor is placed. The plane of the coil is always parallel to the magnetic field, and this length side is perpendicular to the direction of the magnetic field. So that is theta is equal to 90 degree. So the force acting on this side, that is along this vertical, this length side, this vertical side is BIL. BIL. Okay. So that is the value of the force. So we can see F is equal to BIL. Okay. Where B is the intensity of the magnetic field. Now, what is the direction of that force? Now, what is the direction of the force? That we can calculate by using the Fleming's left hand rule. Okay. Put your take your left hand and stretch the thumb, forefinger, and middle finger in the three mutually perpendicular directions, and we place this. The forefinger is in the direction of the magnetic field, and the middle finger is in the direction of the current. Then the thumb will give the direction of the force. So you can see in the present situation, this thumb is pointing inwards. The pointing inwards the screen. Okay, that means the force is acting. The force is acting outwards you. Is acting outwards you. Okay, that is pointing to the screen. So that is the direction of the force. Now look into the other the length side on the other side. That is on the right side. The side is QR. So you can again the current is again the clockwise directions. Now the current is going from up top to down direction, and the field is again along the north to south direction, and again the force is F is equal to BIL. The F is equal to BIL because the length side length L is the length, and I is the same current I flows through the QR side also, and B is the magnetic field. Okay. Now same force is again acting on the right side of the coil. Now what about the direction? Okay. Now we take our left hand, and now the field direction is from north to south direction. So we pointing the forefinger in that directions, and now the current now it is acting downwards, like it flows downwards. So the middle finger pointing downwards. Then in which direction the thumb points? The thumb is pointing you, that is pointing outside. Okay, so the same force FBIL is acting on the right side QR, but its direction is towards you. Okay, that means it is just opposite to the force on the left side, that is outwards. Here the force is acting towards you. So we have the two forces. Okay, what about the top and bottom side? What about the top and bottom side? When we consider the top side PQ, here the current, here what about the theta? Here the length element PQ and the direction of the magnetic field are the same. That means theta is equal to 0. So sin 0 we know is 0. So the force acting on that top side is 0. Similar in the case of the downward in the bottom side. That is SR. When we consider the SR, that is the angle between the the magnetic field and SR is 180 degree. When we consider the PQ, that side is 0, then the SR side it makes an angle 180 degree with the direction of the field. Sin 180 we know 0. So again the force acting on the bottom side is also 0. So out of the four sides of the coil, only the force acting only the two sides. This value is BIL. And but these equal forces, they are acting in the opposite directions. So we have the two forces that's acting in two equal forces in the opposite directions. So they constitute a couple. They constitute a couple. So the whatever the moment of this couple, the moment of the deflecting couple is equal to 1 of the force into the arm length. 1 of the force into the perpendicular distance between the two forces. So you can see this deflecting couple CL is equal to BIL into B. B is the breadth of the coil, that is the distance between the two perpendicular forces. So BIL into B. What is L into B? L into B, that is the length into breadth, that is the area of the coil. So the deflecting couple is equal to BI into capital A. BI into A. Okay. If there are n number of turns, then the total deflecting couple is equal to n into small n into BIA. Small n into BIA. Okay. Now this a torque is acting. And what about the effect of the torque? The effect of the torque is it tries to rotate the coil. Okay, this couple rotate the coil, and as a result, the suspension wire gets twisted. This wire gets twisted. Okay, so here the two forces. One is acting outwards, and another is acting inwards. So as a result, this couple tries to rotate the coil, and as a result, the suspension wire that gets twisted. Okay. So the suspension wire opposes the deflecting couple with a restoring couple. Okay. We know when we try to change the shape of a material, a restoring force is developed, and it try to restore the material into its original shape. Here, when the deflecting couple try to rotate the suspension wire, it try to twist the suspension wire. What will happen? There is a restoring couple developed inside the suspension wire, and it opposes the deflecting couple. Okay. So we have the two couples. One is the deflecting couple, that is CD is equal to N into BIA, and there is another couple which there is a restoring couple that is developed inside the suspension wire. It opposes the deflecting couple. And what about the restoring couple? Suppose alpha is the couple per unit twist of the wire. Alpha is the couple per unit twist for the unit angle twist of the wire. Then, and in our present case, if the wire twisted through an angle, or the deflecting couple rotated the coil through an angle theta, then the restoring couple is equal to alpha into theta. Here alpha is the couple per unit twist, the couple per unit degree of unit angle of twist. Okay, so the restoring couple is equal to alpha theta. Okay, so these two equal and opposites, so we can equate them. That is, the deflecting couple is equal to the restoring couple. So N into BIA equal to alpha theta, or I is equal to alpha divided by BNA into theta. Here all the terms inside the bracket are all constants for a given galvanometer. Here alpha, for a given suspension wire, alpha is a constant. For a permanent horseshoe magnet, the B is a constant. N is the number of turns. That is, once we constructed the galvanometer, the number of turns and its area are constants. Okay, so the bracket, all the terms inside the bracket form a single constant. So we can say I is directly proportional to theta. The current I passing through the galvanometer is directly proportional to the deflection theta. Okay. So when we can measure the value of theta, then we can calculate the current through the galvanometer. So this deflection theta can be measured using a lamp and scale arrangement. Here we have a mirror in the on this suspension wire, and about a 1 meter distance we place a lamp and scale arrangement. That is, the light from the source, the lamp, it 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 reaches the mirror and it gets reflected, and the reflected spot that can be obtained in the a transparent, semi-transparent scale. So these lamp and scale are placed at a distance about 1 meter from the galvanometer. Okay, and when the coil rotates, the suspension wire gets twisted, the mirror also twisted. So when the mirror rotates, what happens? Here the reflecting spot, this spot of light is also deflected. That is deflected along this scale. So before starting the experiment, we are arranging the reflecting spot coincides with the zero of the scale. The zero of the scale. So when the current passes through the galvanometer, the coil rotates, and the wire twisted, and the mirror also twisted, and the position of the reflecting spot gets deflected. Okay, so we can directly measure the deflection, how much distance, and we can calibrate for this much distance. The current through the galvanometer is this much. Okay, so when we calibrate, we can directly measure the current from this arrangement. Okay, so that is the working of the moving coil galvanometer. Okay, instead of a lamp and scale arrangement, suppose if a pointer is fixed at the lower end of the suspension wire, that you can see in the figure. In the bottom figure you can see, if instead of this wire suspended, and so all these arrangements we can remove, and here also there is a coil is there is a magnet is there, and here in the bottom part, the suspension wire, lower end of the suspension wire, we can fix it a pointer with the help of a hairspring. Then when the current passes through it, the coil gets deflected, and this pointer also deflected. So with the proper calibration, we can measure the current directly from this calibrated scale. Okay, so this is we call the table galvanometer. This is a table galvanometer. Okay, so in that also, here the current through the galvanometer is directly proportional to the angle theta. Okay, now let us see what are the factors on which the sensitiveness of the galvanometer depend. Okay, so we know I is equal to alpha divided by BNA into theta. Okay, to increase the sensitiveness, we have to measure, we have to increase the suppose we have to measure the very smallest current. We have to measure the very smallest current. So for the very smallest current, there should be a large deflection. That is the sensitiveness. Okay, so how can we increase this value? So increase in the n, the sensitiveness can be increasing by n. Okay, so if we increase the number of turns, we can measure the small value of the current. That is, we can increase the sensitiveness. Okay, so we can increase the number of turns, we can increase the sensitiveness and increase the area of the coil and increasing the strength of the magnet, that is the intensity of the magnetic field, and by decreasing the alpha, the couple per unit twist of the wire. Okay, so by making this, we can increase the sensitiveness of the galvanometer. And what are the disadvantages of this galvanometer? The advantage is we can measure the very small value of current with this type of moving coil galvanometer. Okay, but the main disadvantage is that it is a very delicate instrument and it requires a permanent installation. It is a very delicate instrument and it requires a very permanent installation. Okay, that is one of the disadvantages. And as we have already discussed, this moving coil galvanometer can be converted into a tabletop by the coil can be by pivoted the coil on a jeweled bearing and providing a restoring couple by hairspring coupled by a hairspring made of phosphor bronze. But we can make them as a table galvanometer, but its sensitiveness is very much decreased. I think we can see an animation regarding the working of the moving coil galvanometer.
Moving coil suspended type galvanometer. Galvanometer is a device used for measuring feeble current accurately. It is also known as electric current detector. Moving coil galvanometer works on the principle that when a current carrying coil is placed in a magnetic field, it experiences a torque. This torque that is produced is proportional to the current passing through the galvanometer coil. Construction. Shown here is the moving coil suspended type galvanometer. Click on the image to view the internal parts. A moving coil galvanometer consists of a coil PQRS. This coil is made by winding a long insulated copper wire on a frame of a soft iron core. The coil is suspended between the pole pieces of a magnet. The suspension is done with the help of a thin phosphor bronze strip. The upper end of the strip is connected to a movable torsion head. The lower end of the strip is connected to a hairspring. There are two terminals, T1 and T2, connected to the source of current. The concave mirror M, used for measuring the deflection, is mounted above the coil. This mirror moves along with the coil. The deflection in the coil is determined by a lamp and scale arrangement. The entire arrangement is enclosed in a non-magnetic case with glass windows to avoid disturbance due to air. 3 leveling screws at the base are used to level the apparatus. Working. When a current I is passed through the rectangular coil PQRS, the coil rotates due to a torque. Torque is equal to NIAB sin theta. The magnetic field is always parallel to the coil, and hence the angle between the normal to the plane of the coil and magnetic field is 90 degrees. For a radial field, torque is equal to NIAB. This torque deflects the coil, producing a twist in the suspension strip. A restoring torque equal to k theta is set up, which tries to restore the position of the coil, where k is the restoring torque per unit twist, also called torsional constant. When in equilibrium, restoring torque is equal to deflection torque. NIAB is equal to k theta. I is equal to k theta by NAB. I is equal to g theta. G is called the galvanometer constant and is equal to k by NAB. Therefore, we see that I is directly proportional to theta.
Okay, I hope all of you have well understood the working of the moving coil galvanometer. Next we are going to see how a galvanometer can be converted into a ammeter. We know ammeter is an instrument that used to measure the current. In order to convert a galvanometer into an ammeter, a suitable shunt resistance is connected parallel to the galvanometer. We have already studied what is a shunt resistance. So, shunt is a very low resistance connected parallel with a sensitive galvanometer to reduce its sensitiveness and protect it from heavy currents. The shunt resistance bypass the most of the current that we are going to measure, thereby protecting the galvanometer. At the same time, we can measure the current through the galvanometer. Let us see how it works. In the figure you can see this is the galvanometer, and we are connected a shunt resistance S parallel to the galvanometer and is connected to a source of current. Now there is a battery. Now the current from the battery, that is I, that is when it reaches this junction, it is split into two. One part is, that is IS, is going through the shunt resistance, and IG, that is going through the galvanometer. So we should keep in mind that I is the current that we are going to measure using the ammeter. That is, suppose it is a 5 ampere galvanometer. So 5 ampere is the maximum current that we are going to measure using the ammeter. So converting the galvanometer into ammeter, we should bear the value of the maximum value of the current. So according to which we are going to connect and we are going to choose the shunt resistance. Okay. Now, since the galvanometer and the shunt resistance are parallel, the potential differences across the galvanometer and shunt are the same. Okay. Now, here I is equal to the total current. I is equal to Ig plus Is. From that, Is is equal to I minus Ig. Okay. Since the potential difference across the galvanometer and shunt are the same, I can write Ig into G, that is the PD across galvanometer, is equal to Is into S, the PD across the shunt resistance. So let us replace Is by I minus Ig. So Ig into G is equal to I minus Ig into S. Let us express all the terms that is related with the Ig into one side. So Ig into G plus S equals I into S. Okay. From that, Ig is equal to, the current through the galvanometer is equal to I into S divided by G plus S. That means only S is a very small value, is a shunt resistance, it has a very small value of resistance, divided by G plus S. G plus S, that has a very higher value. Okay, that means only a very small fraction of the main current flows through the galvanometer. That is, I is the main current. So, and S divided by G plus S is a very small fraction. That means the only very small fraction of the main current I is flows through the galvanometer. That means Ig is a very small. Okay, but S and G are the constants. For a given setup, S and G are the constants. Then Ig is proportional to I. Ig is proportional to I. That means even though the value of Ig, the current through the galvanometer, is only a very small fraction of the total current to be measured, at the same time that value of Ig is proportional to the main current. Okay, so with the proper calibration, we can measure the main current. We can measure the main current that we are going to measure using that instrument. Okay, so with the help of the shunt resistance, we can bypass the most of the current. At the same time, the current through the galvanometer is proportional to the main current to be measured. In that way, we can convert the galvanometer into ammeter. Okay, so what is the value of the shunt resistance to be connected? That can be calculated using this formula. From this formula, Ig is equal to I into S divided by G plus S. From that, we can have the expression S is equal to Ig into G divided by I minus Ig. Okay, Ig into G divided by I minus Ig. So the value of the shunt resistance to be connected is depends on the safe value of the current that can pass through the galvanometer, that is Ig, and is resistance and the main current. Okay, so when we design a galvanometer, for the conversion of a galvanometer into an ammeter, we should know what is the range of the current that we are going to measure, whether it is a 2 ampere ammeter, whether it is a 5 ampere ammeter or 10 ampere ammeter, and according to which we can choose the suitable value of the shunt resistance. Now next, we are going to convert a galvanometer into a voltmeter. So voltmeter is an instrument that used to measure the potential difference across any electrical elements. So to convert a galvanometer into ammeter, to convert a galvanometer into a voltmeter, a suitable high resistance R must be connected in series with it. So for conversion into ammeter, we are connecting a very small resistance, that is a shunt resistance, parallel to the galvanometer. For converting a voltmeter, for converting into a voltmeter, we connecting a suitable high resistance R in series with the galvanometer. Okay, let us see how it works. So look into the figure here. In series with the galvanometer, a high resistance capital R is connected, and E is the battery, and Ig is the current through the galvanometer. Okay, so when we connect a galvanometer, when we use the galvanometer, we should care about the maximum value of the current. The current through the circuit should be less than the safe value of the current that a galvanometer can handle, because galvanometer is a very sensitive instrument. Okay, so look into the figure, and we can have by the Ohm's law, the current through the Ig, the current through the galvanometer Ig is equal to, by using the Ohm's law, I is equal to V by R. Okay, here E is the source potential, so E divided by, since these two are in the series connection, the total effective resistance equal to R plus G. So E by R plus G is equal to the current Ig. Okay, or E is equal to Ig into R plus G, or E is equal to Ig into R plus G. So for a given setup, both R and capital G are the constants. Okay, for a given instrument, these two are the constants. Then we can see the E is directly proportional to Ig. So in that case, the current through the galvanometer is directly proportional to the potential difference. Okay, so in that way we can this instrument will act as a voltmeter. Okay, so the value of resistance, as in the previous case, the value of the resistance R to be connected in series with a galvanometer to read a voltage up to E, that can be obtained by using this relation, that is capital R is equal to that we can obtain from the first equation. Capital R is equal to E divided by Ig minus capital G. So the value of R depends on what is the range of that voltmeter that we are going to use. That is, suppose it is a 2 volt voltmeter or 10 volt voltmeter. So that is the maximum value of the value of the voltage that we are going to measure, that is E, and G is the resistance of the galvanometer, and Ig is the safe value of the current that a galvanometer can handle.